Okay, this video is a review for the AP gas law test review, and so these problems are kind of like some of them are similar to some that are on the test. Okay, so the first problem is you have to find the molar mass of a gas. Okay, so molar mass. So to find a molar mass, so a molar mass equals you have to find the grams of the gas divided by the moles of the gas. And if you look on the problem, it's telling us the grams right here, 0.1298 grams. Okay, now what we have to find is we have to find the moles. Okay, now if you read this problem, they give you a bunch of gas law data like pressure, volume, temperature. So that means you're going to use PV equals nRT. But one thing about PV equals nRT, you always have to make sure everything's in the correct units. For example, the volume, okay? The volume is 71.8 milliliters. So whenever you're using the PV equals nRT, you always got to be in liters. So you're going to change to liters. So 1 liter, 1,000 milliliters. So that's going to equal 0.0718 liters. Okay? We're looking for moles. That's the moles. And then the pressure, well, the pressure is given in millimeters of mercury, so that's 774.45 millimeters of mercury. But whenever you collect a gas using water displacement, all right, and so they give you the vapor pressure of water, what they want you to do is they want you to take that away because the vapor pressure of water gets in and affects the pressure, and to get the pressure of the gas that you want, you have to subtract the vapor pressure of water. And so if you do that, that equals somewhere around 755.75 millimeters of mercury. Okay, because we're working in millimeters of mercury, we have to use the R value, which is the 62.36 millimeters of mercury times liters divided by moles Kelvin. That's on your gold formula sheet. Okay, so we want to match the R value to our pressure value. And then the temperature is 21.5 degrees Celsius, but we have to work in Kelvin. So you're going to add 273. And if you add 273, you get 294.5 kelvins. Now, once you get everything in the right units, we can take this PV equals nRT. I prefer to rearrange it, divide both sides by RT with the variables, and then I get N equals PV over RT. That's how we're going to get the moles. So then I'm going to plug in N equals P, 755.75 millimeters of mercury, times V, 0.0718 liters, divided by the R value, 62.36 millimeters mercury times liters, divided by moles Kelvin. Now, whenever you plug in the R value, it's a good time to look and make sure that your units are matching. Millimeters of mercury, liters. Okay, we're looking for moles, and our temperature should be in Kelvin. The R value is just a reminder to have all the units in the correct units. So then if you do the math with this, you end up getting something like 0.00295 moles. Okay, now that's not the end of the problem because it wants the molar mass. So you got to come back up and take the grams and you divide it by the moles, and you end up getting, if you do this math, I think it's around 43.9 or 44 grams, 43.9 grams per mole. Okay, here's another problem. This is very similar to the one that was on AP Free Response 2012. And so basically they're taking a hydrocarbon. So a hydrocarbon is a CH, some sort of gas. Okay, we don't know what the C and the H are. They're reacting that with oxygen, and it's going to make CO2, and H2O. Now, what it wants us to get, it wants us to find the total pressure in the container when the reaction is over, and it wants us to write the balanced equation. All right, so what I think is helpful when we're doing this is to make an ice table. So I'm going to make an ice table to help me keep my data straight. All right, so initially, if we look at this, so the ice, so initially the CH, so they're putting in 0.950 atmospheres. Okay, and remember you can do this because the pressure will be proportional to the moles as long as the volume and the temperature are going to stay the same. So anyway, and then they're putting in 12.50 atmospheres of oxygen, and initially there's 0 and 0. Now, they're sparking the container. So after they light this on fire, okay, they said that excess oxygen remains, and that pretty much means that all of the CH4 reacted, so it's going to go down by 0.950. And so that means there's 0 of that left. We don't know yet what this is going to go down by, but it does tell us that this goes up by 7.60 and this goes up by 8.55. So at the end of the reaction we have 7.60 and 8.55. Okay, now there is excess oxygen that remains. So now what we got to do is figure out how much oxygen was actually used. So we can just do a little math here. So here's the thing to think about. So for O2, when O2 forms CO2, all right, so forms CO2, you can think of it this way. For every 1 atmosphere of O2, see how there's 2 O's there? You would be able to make 1 atmosphere of CO2. So what you can just do is you can do this here. You can say, well, I got 7.6 atmospheres of CO2. So for every 1 atmosphere of O2 that reacts, you get 1 atmosphere of CO2. And so to make that 7.60, you're going to need 7.6 atmospheres of O2. So we know that this is going to go down by minus 7.60. That's just to make the CO2. Now we can do the same thing for the H2O. So if we have O2, remember, one of those, okay, and well, let's not do one, well, I guess we can do that, but anyway, HOH, that's H2O. So one O2 can make 2 H2Os in terms of the oxygen. See, for every one of these, you can get 2 of these. So you could take this 8.55 atmospheres of H2O, and then you can do this. You can say for every 2 atmospheres of H2O that are formed, you need 1 atmosphere of O2. And if you do that math, it equals 4.275. Now I'm not going to round off to significant digits yet. I'm just going to keep that in there. So this is going to go down by 4.275. Okay, just to make the H2O. So this much to make the CO2, this much to make the H2O. So the total amount, if you add these two together, I'm just going to write it over here, is the O2 is going to go down by 11.875 in total, okay? The amount to make the CO2 and the amount to make the H2O added together makes 11.875. So at the end of the reaction, the amount of oxygen that's left over is 0.625. Now, we can determine the total pressure in the container after the reaction is complete by just adding together the pressures of everything at the end. So you would take 0.625 atmospheres plus 7.60 atmospheres plus 8.55 atmospheres, And if you add that all together at the end, you get 16.775 atmospheres. Okay, now to balance the equation, you got to look at how much actually reacted. We know that there's 0.950 atmospheres of this that reacted. There was 11, now this is the tricky one, there is 11.875 that actually reacted, not the total amount, but the amount that actually reacted. That's important. You know that this much was formed of the CO2, and you know this much of the H2O was formed. Now, you need to put that in the simplest whole number ratio, and you just basically you divide the smallest number by itself, and you divide this number by the small number, you divide this number by the small number, and you divide this number by the small number. That's supposed to be 0.950. My pen's kind of acting up a little bit. And so when you do that, when you divide the small numbers by themselves, or by the numbers by themselves, you end up getting a 1 here. You end up getting 12.5 here. You end up getting 8 here. And you end up getting 9 here. But you can't have an equation with 9.5 or 12.5 there. So basically you have to double everything. And so the balanced equation that you end up getting at the end is basically 2 and 12.5 times 12.5 is 25. So I'm just going to write that here. And then 8 times 2 is 16. And 9 times 2 is 18. And then you can say, hey, there's 8 carbons, so that's, you put an 8 here, and then 9 or 18 times 2, so that's going to be 18 there. Okay? Okay, next one. This one is one that's helpful to draw a picture, but first you need a balanced equation. So C3H8 plus O2 makes CO2 and H2O. So if you balance this equation, there would be a 3 here, and then a 4 here, and then 6, and 4 is 10, and a 5 here. So this is just the mole to pressure proportionality. So the C3, H8, and O2, when those two are in the container, so here's my container, the pressure is 3 atmospheres. That pressure is caused by 1 plus 5, 6 moles. So 6 moles is causing 3 atmospheres. Now, after the reaction, if all this completely reacts, we have the same container, okay? We don't know the pressure, so the pressure we don't know, but we do know that after it's over, there would be 7 moles, according to 3 plus 4. So this is just a proportion, because the moles are proportional. 3 atmospheres caused by 6 moles of pressure will be equal to blank atmospheres, so we'll call that X atmospheres, and 7 moles of particles. So cross multiply and divide, you end up getting that X equals 3.5 atmospheres. Okay, number 4 is a pretty simple problem, but it seems like people miss it on the test. I don't know why. So, okay, a gas pressure contains 3 atmospheres of helium. Okay, now they're adding hydrogen gas, so they're adding so much hydrogen until the pressure in the container, if you add them together, so 3 plus what is going to equal a total of 12 atmospheres. Well, that must be 9 atmospheres of hydrogen, because the partial pressure of each must equal the total. Okay, here's another problem that isn't too tough, but people sometimes miss it. Okay, and so basically this one is they want you to find the partial pressure of nitrogen gas, but they're giving you a mixture of the gases. So there is a formula on the formula sheet, and you could write it like this, that the pressure of nitrogen will equal the pressure total times the moles of nitrogen over the moles total. That's supposed to be moles total. So what you would do is you would say, okay, I want to find the pressure of nitrogen. So the pressure total is 12 atmospheres. Now what you got to do is you got to figure out the moles of nitrogen and the moles of oxygen and figure out the total. So there's 28 grams of nitrogen, and 1 mole nitrogen is 28 grams nitrogen. So basically you have 1 mole nitrogen. And then you're going to do the oxygen. You have 64 grams O2, and 1 mole O2 will be equal to 32 grams O2. So 64 times 1 divided by 2, that's 2 moles oxygen. Now, you have to get the total moles. Don't forget to do that. So that's 3 moles total. So we're going to take this 12 times, okay, our moles of nitrogen, which ends up being 1 mole. I guess my pen quit working. But anyway, you would see that it is 1 mole. All right, and sorry I can't finish this, but 1 over 3. So 12 times 1 divided by 3 would be equal to 4 atmospheres. The answer to this is 4. I'm sorry, my pen quit working, but that's what we're going to say that it is. All right, that's it for this these review problems. Sorry I couldn't finish the last one, but I guess I can write with my computer, which is going to be messy, but you would take 1 and divided by, so 1 mole N2 divided by, sorry, I don't know how to stop it, 3 moles total. And so the answer, and I just don't know, I can't stop it. But anyway, so 12 times 1 divided by 3 equals 4. That's it.